Let's talk about VTP next. This is enough to understand. This is a proprietary protocol of Cisco. We don't use it very much in the enterprise network now. Except for exams. When you are preparing for the exam in the future, we'll send you the document. Just enter 3 commands when you face. This thing is not very important. VTP is called Virtual LAN Trunk Protocol. It is used to create VLANs in batches. You can see. There is a server here. There is a client. Indicates that this is a CS architecture. If there are many switches in the enterprise. Assuming 100 switches. But what if you have 1000 VLANs? Too much work. You have to manually create 1000 VLANs on these 100 devices. Then we can now choose a switch as server. Others are treated as client. I configure VLAN on this server. Then sync to other devices. Reduce workload. We'll get to that later. Cross-VLAN intercommunication between Layer 3 VLANs. Let me briefly talk about how to configure it. It's enough for everyone to understand. First we enable VTP. I change a VTP mode. It changed to server. It changed to client. They assign a password to each other. Name each other. It creates VLAN here. It can be seen here. This thing is not needed now. For the client. It cannot create VLANs by itself. Only it can create. Okay. We're done talking about VLANs. Then we look at the next requirements. Actually, VLAN can divide the broadcast domain. That is, there is no communication between different VLANs. Neither unicast nor broadcast. But it also limits the ability of the host to communicate at layer 2. After we divide the VLAN hosts between different VLANs, there is no way to communicate with each other on the second floor. They are not mutually imitable. So I just told you. For the entire VLAN. It's more about wanting to isolate broadcast traffic. And to differentiate and isolate overall data. For example, for different departments, I can rely on VLANs to differentiate different traffic. Make it impossible for them to complete mutual visits. But in fact, in our daily practical application, there will also be a need for mutual visits between hosts. We tend to be more treat VLAN as a means of security isolation. But usually, sometimes we also want to exchange visits between hosts. That is, I hope the host unicast can still communicate. We want more to suppress its ability to broadcast. Therefore, the VLAN we refer to hopes to make it unreachable between the 2 layers. But we hope that there is still communication between the 3 layers. That is, we want the 2 hosts to be in different VLANs. However, it is still possible to communicate data. Switch-based networking. Isolation of broadcast traffic through VLAN. Then by itself it can narrow down the scope of the broadcast domain. What if unicast communication is desired between devices across VLANs? Can't it work? That is to say, we hope to realize layer 2 broadcast failure. But it is hoped that unicast between different VLANs can be communicated at other levels. If we want to discuss the issue of unicast, we also discuss on the second floor. Neither unicast nor broadcast. If I want the host to communicate now, it can only communicate across network segments. That is to say, only rely on the switch to query the MAC address table. Corresponding VLAN. Corresponding interface. Forward accordingly. This is not working anymore. You can't complete the communication. So now we can only communicate across network segments. If communicating across network segments, it is known. Access as a host across network segments. is looking for a gateway. The gateway helps it communicate across network segments. Then we have to mention devices such as routers. Wait a minute, I will introduce a router. We will use a representation of a router across network segments. Routing table. Everyone should be familiar with this. But we all know. Now this is the basic forwarding of some addresses. We can find gateways across network segments. Then the router directly looks up the table and forwards. But now there are more VLANs. How can we communicate with each other on top of VLAN? This is called mutual access between VLANs. Inter-VLAN access needs to use the routing function. Between different VLANs. There is no way to communicate on the second floor. If you want to communicate, it can only be forwarded with the help of three-layer query routing table. So, we can achieve, even after deploying VLAN, we can still communicate across network segments. This is an effect we want to achieve. It has several ways to implement. One of the easiest ways. This thing is not commonly used. Called one physical connection per VLAN. Let's see how it goes. The PC on the left is assigned to VLAN 2. This is an access interface. Belongs to VLAN 2. The right side is divided into VLAN 3. This is an access interface. Belongs to VLAN 3. Router as a layer 3 device. Its interface is a layer 3 interface by default. It has no way to process data carrying VLAN tag. So the switch is connected to this interface of the router. It must also be an access interface. These two must also be access interfaces. So how do host A communicate with host B? They cross VLAN. I can choose a method. Is to configure the access interface on both ends of the switch. And both of them are VLAN 2. Both of them are VLAN 3. As a different VLAN. Under normal circumstances. I now send a broadcast data. So broadcast data comes in here first. Can go out here. Get to the router interface here. Router interface does not forward broadcast traffic. So the broadcast data will be isolated here. So this data can't reach here. Secondly, if I send a broadcast data. So here you go. Mark VLAN tag 2. Then it has no way to send out from VLAN tag 3. So this data cannot reach host B. I want to send a data in the future. If it is a broadcast data then. In fact, it can only be circulated in the entire VLAN. I can't send it to host B. Because it is isolated by VLAN. These two interfaces are on different network segments. You have to distinguish this. If we want to communicate at layer 3. To use routing. A router is two interfaces and two network segments. So the two of them are not on the same network segment. Assume that host B is in the 1.0 network segment. Host A is the 2.0 network segment. Host B wants to access host A. Layer 2 communication between different VLANs is definitely not possible. So it has to go 3 floors. Layer 3 traffic must reach the router. Let's talk about the process. Traffic sent here. The interface of access is marked with tag 3. And go from here with 3. This is an access interface. Come out, strip off 3. Then go into the router here. So what the router receives is a complete data. Go to the 2.0 network segment in the future. RA queries the local routing table. It is found that the 2.0 network segment is sent from the local interface. The next hop is this interface of host A. It comes out. It also sends out a blank data frame. Go here and put VLAN tag 2. Come out from here and remove VLAN tag 2. Then send to host A here. That is, all interfaces are access interfaces. Only the switch is configured here. Both of these are tag 3. Both of these are tag 2. Tag 3 and remove tag 3 here. Tag 2 and remove tag 2 here. When the final data passes through these devices are blank, it can isolate the communication between the hosts at the second layer and help them communicate at layer 3. But you will find a problem. When we are communicating at layer 3, these two hosts actually cross the network segment. I will explain to you. You will find, when we were doing the experiment just now, usually when we are doing layer 2 VLAN experiments, we all prefer to put it on the same network segment, because it's easier to say. Let everyone intuitively see some of its corresponding problems. But in fact we are working in real. Different VLANs will be divided into different network segments. I give a simple example. If you want to exchange visits between different VLANs, we first need to use the 3-tier function. That is routing. Because on the second floor we only check the MAC address table. We just looked at the MAC address table, VLAN ID, interface, and MAC address. They are indispensable. As long as the VLAN is unreachable, absolutely no access to the second floor. So the second floor can't move. Only 3 floors. If it is a 3-tier routing, then everyone should know. For example, I divide host A into VLAN 10. Assign host B to VLAN 20. And they are both on the same network segment. You have to think about a question. If the same network segment, it wants to access a device like this, it sends an ARP broadcast request. Directly request the other party's MAC. Then it is impossible to communicate directly. Because it now sends the broadcast. Will not reach this device. That is to say, is unable to communicate. I can't get through the second floor. When you are encapsulating data, you will let this PC directly access. Request its MAC. Then you can't go. Because the data cannot come through. Request if the data is not available. Unable to encapsulate MAC. So if it is across VLAN, you are also configured to the same network segment. It can't communicate. We only have one way now. We go 3 floors. Access between 2 PCs across network segments. You have to configure the gateway for them. Often routers forward across network segments. It is impossible for you to configure the same gateway address for 2 devices. That is, if 2 devices are in the same network segment, gateway cannot be configured. So, we forward data across network segments. It is often configured as different network segments. For different VLANs, you have to walk 3 floors. You let this data request the gateway's MAC. Data must first reach the gateway to check the routing table. So we are on the project. Usually it will be divided into different VLANs and divide into different network segments. This is the gap between our experiments and real applications. The above mentioned is a physical connection per VLAN. When you learn NP in the future, you will talk about ARP proxy. In the future, there will be an ARP proxy in the VLAN. We only learned one ARP proxy in the NA phase. Is the easiest one. Then you will know that there are other ways to achieve. Let's look down. Let's go on to talk about a slightly more complicated knowledge point. One-arm routing. The difference between the single arm and the picture just now is that there are 2 lines in this graph. This picture has only 1 line. 1 physical connection per VLAN. It is called a line for each VLAN connected to the router. This has a router interface. One-arm routing refers to the. This is only one to undertake the traffic of multiple VLANs. In the future, there will be more than just these 2 flows. Can be VLAN 4 or VLAN 5. Can connect. Then all go this line. Single arm with only one line. Let's talk about how it's done. There is a trunk written here in the middle of it. Different from before. Just here is access. Now is the trunk. So the configuration of the trunk is demonstrated here. I just told you. The interface of the router is a layer 3 interface. It doesn't recognize anything about the tag. If configured as trunk here, trunk is released for data. Then when the data is sent, if their current native VLANs are different, it may be posted with a tag. Now this interface is not recognized. So it creates some problems. Everyone should know. The interface of the router is a layer 3 interface. It cannot configure layer 2 VLAN. Therefore, the layer 3 interface does not recognize the tag by default. It has no way to receive and forward data. But one such implementation is shown in the figure. That means it will definitely come true. The interface of the router does not recognize the tag. I want it to recognize. At this time, the physical interface of the router is not working. We can make a logical interface for it. Then I can, based on a physical interface, give it a few logical subinterfaces. For subinterfaces, I can under a physical interface. Based on it has many subinterfaces. Let these subinterfaces serve different VLANs. Like this picture. 2 interfaces on 2 routers. We now let an interface of a router use as 2 subinterfaces. What are the characteristics of this subinterface? First, it can configure the IP address normally. To us, the host has to configure the gateway. Configured on subinterfaces. It can be configured with IP normally. Secondly, this subinterface can also have layer 2 functions. That is, it can handle tags. Now means that only one line in the middle will be able to complete. Trunk can be done between them. Let me briefly talk about the function of the subinterface. It now receives a data. This is the access interface. Tag 2 here. Through this router. We then proceed to the trunk interface. Suppose its native VLAN is 1. Came out 2. Then when carrying such data with tag 2. When entering this subinterface, the subinterface can receive tagged data and strip the tag. It has the ability. Simultaneously, another subinterface can process the data of VLAN 3. That is, it now looks up the table. It now goes from segment 2.0 to segment 3.0. After checking the local is a direct route to come out from another subinterface. When it comes out, add another subinterface VLAN. Is tag 3. Then send. Pass through the trunk interface of the switch. Then when passing through this access interface, strip off the tag. Then forward to host B. Complete the communication between the two of them. Is equivalent to. We extended this interface to it. In this way, the problem of insufficient router interfaces can be alleviated. But in this case, it will have some other problems. We have another way. Layer 3 switching. Well, first you need to know. There are actually a lot of problems with one-arm routing. So it's not very common in corporate networks. May be seen in small businesses. Medium and large enterprises do not use it for a long time. Because it's very unoptimized. Including many switches now. In fact, it's all 3 layers of switching. So now one-arm routing is rarely practical. But we have to learn it. This knowledge is very important. First, its first question. Single point of failure. That is to say, once this thread is broken, you will find all business is now closed. This is still 2 VLANs. Both VLAN 4 and VLAN 5 can be connected to the switch. Then between all these VLANs, all visits to be made follow this line. If this thread is broken, it will not leave. This is the most important question. Single point of failure. Second, for the router, it will have additional performance loss. The main function of a router is to responsible for IP addressing and forwarding. This is in terms of 3 layers. Address forwarding is a router in itself. This processing tag. This is not someone's job. So where are you now? For our router, configure the function of the second layer on it. Then there will be some additional loss on it. This is the second point. And a third point. This link will have certain congestion problems. That is, the current communication traffic between VLAN 2 and VLAN 3 go this way. In the future, if you access other VLANs, you will not take this route. There will be a lot of traffic on this road, been piled on this one line. This is pretty much the same as the single point of failure problem. Interaction between all traffic. All follow this line. It is not optimized. So one-arm routing will have such a problem. So how to solve it? One of the most common ways we use now. Layer 3 switching. That is, stop letting the router do the job. Why add a router here? Just want to have its routing function. I want to configure an address for it. I want to configure a gateway for the PC below. Configured on this router. Then just get a switch now. Let the switch function as a router. That is, this switch can be used as a layer 2 switch. Layer 3 routing function can also be added. The routing function is to give the interface PIP. And as the gateway below, it has a routing table. Just complete the lookup table forwarding. It just wants to configure an IP to check a routing table. So it doesn't need a dedicated router. As long as the switch can do the job. So now there are new devices. Layer 3 switching. For switches, it is now a layer 3 switch itself. It has certain 3-layer functions. It has its own routing table locally. And we can configure IP under the VLAN interface of the layer 3 switch. We can enter the VLAN 2 interface of the switch. Give it an IP address as the gateway of this 2.0 network segment. I can enter the VLAN 3 interface of this switch. Give it an IP address as the gateway of this 3.0 network segment. Then when we go to data forwarding, PC directly accesses across network segments to find the gateway. You can understand it as this switch. It has a fake router inside its body. This router also has its own interface. This interface is called SVI. This is the virtual interface of the switch. There is a routing table in the router. The router has its own interface. This interface is a VLAN interface. Let's look directly at the configuration. Let's first configure this one-armed route. I deleted this device. Turn it off too. Wait a minute, I reconfigure. Then I add a router in. The router needs to be connected to this device. If you want to add wires to the equipment, you have to turn off this device first. Otherwise, the device cannot be connected. And I tell you, after you have created on the switch, even without saving the configuration, this VLAN is still there. I open it. After opening, we are going to configure an IP address for this device. 192.168.10.1. Both of them have to cross network segments. Otherwise, there is no way to configure a gateway for it. It belongs to VLAN 10. Then it will have a gateway. 192.168.10.254. Configure PC22. 192.168.20.1. 24-bit mask. Next configure the gateway. 192.168.20.254. OK. This is their address plan. Then I'll reconfigure them. One arm is. Now when the router is connected to the switch, use only one interface. This arm carries the traffic of multiple VLANs. So let's revisit. For routers, one of its interfaces must be able to handle VLAN 10 and VLAN 20 data. The data of VLAN 10 is handed over to one of its subinterfaces for processing. The data of VLAN 20 is handed over to one of its subinterfaces for processing. We can configure them differently. We need to change the PC address. This is PC1. This is PC2. This is the switch. Slightly slower. This is the homework I left for you today. So when I configure, everyone should look carefully. The IP address is 192.168.10.1. 24-bit mask. Then we need to configure a gateway for it. 192.168.10.254. This is PC1. Next look at PC2. IP 192.168.20.1. Mask is 24. Gateway is 192.168.20.254. Two PCs are configured. Then we come to the switch here. Show VLAN brief. Let's check if there are these two VLANs. Have VLAN 10 and VLAN 20. But you will find the interface we divided just now is gone, because it restarted. But how does it save the command on the switch now? Then let me tell you. Type right here. Then press enter and it's OK. We go to the switch. A VLAN has been created on the switch. We can directly divide the interface. E00 interface. This is the interface connected to PC1. Divide into VLAN 10. Switch port mode access. Then, switch port access VLAN 10. Then we enter the E01 interface. It is connected to PC2. We should change the mode to it first. Switch port mode access. After that the difference is. This time the VLAN should be written as 20. After that, we have to go to the 02 interface again. This is the interface connected to the router. Before we change its mode to trunk, we are going to enter a command. Switch port trunk encapsulation. This is an encapsulation mode we have carried out. Then enter a question mark. We have two common. One is called .1q. One is called ISL. .1q is the public mode I just told you, called 802.1q. ISL is proprietary in Cisco. We use ISL by default. So we manually change it to .1q here. Now we are going to use .1q. For example, many real machines with newer mirror images. You don't need to enter this command. But there are some old equipment. Still have to enter this command. In the emulator if you don't type. Instead, go directly to modify the schema. It will report an error. Before you enter mode trunk. To enter this command first, change its mode to .1q. Because the image of many new Cisco devices is directly .1q. No more ISLs. Then under the interface, We can give it a pass on 10 and 20. In fact, it is allowed by default. Let's take a look. Switch port trunk allowed VLAN. I put a question mark here. For example, I want to add a certain VLAN now. To allow it to pass, just write add. More commonly used is all. Is to let all. Word means that you can write which one you want to release. This except is. For example, if you want to deny a certain VLAN to it, just don't let it go. Then just add what you don't want it to pass. I pass 10 and 20. Separated by commas. Do show run interface E02. Let's check. We can see now. We modified the overall model to .1Q. Changed to trunk. Then released 10 and 20. Here is some simple configuration we did. This does not mean that you have to type. I'm just showing you. Only the two commands to change the mode must be entered. Our switch is actually done. We just need to change it to trunk. Then release 10 and 20. In fact, it will be released by default. Then we're coming to the router. The router will do more operations here. When we are doing one-arm routing, subinterfaces of the router will be used. So before you use the subinterface, first thing you have to do is to enter its physical interface. Interface E00. After entering the physical interface, just open it. No shutdown. After opening, show IP interface brief. We did not configure IP for this interface, but I can also open. Here we have to configure the gateway for the PC below. On the subinterface. Subinterfaces serve different VLANs. How to distinguish which VLAN it serves. Then we have to create subinterfaces and specify which VLAN it belongs to. The router cannot receive tagged data. So actually, there are subinterfaces before the router enters the inside of the frame. In fact, just remove the VLAN tag for it. Subinterfaces can handle VLAN tags. Accessing the subinterface is also simple. Interface Ethernet 0.1. Enter a question mark. This point is usually consistent with the VLAN below. So many subinterfaces. It's all a range you can define. So this has nothing to do with the VLAN below. But usually, we will write a few subinterfaces for the VLAN. It is VLAN 10. Write 10 later. Press enter. You can see. I'm in the subif now. Let's check. Do show IP interface brief. We'll find out. There is a 00.10 in this list. It is also in the upstate. So this is what we call a subinterface. The subinterface has been created. After creating, we are going to configure the address for it. Before configuring the address, we first have to enter a command. We're going to assign .1Q to it too. Then we write a 10 in the back. The meaning of this 10 is different from the 10 above. Here's this 10. It refers to. Now this subinterface has the processing capability for VLAN 10. Tag VLAN 10 here in the future. When passing here, I am here if I write this command. Then it can strip the VLAN 10 tag. So this VLAN 10 actually operates on the tag. So the 00.10 we just wrote. It's actually nothing. It is just to identify that the bottom is now VLAN 10. No matter what to write. will not affect the results of today's experiment. It's just that it's easier to remember when we write like this. OK. We press enter. The subinterface can process the data carrying the tag. Anyone who comes in will strip the tag. Anyone sent from here will be tagged. This is our stripping of the tag. If we want to achieve PC cross-network segment mutual access, it must be configured with a gateway. The gateway address is configured on the subinterface. 192.168.10.254. Open it. Opening is a habit. In fact, it is enabled by default. Because you opened the physical interface. It opened. But I hope you will develop a good habit. Make sure this interface is open. Afterwards, we also configure the 20 interface in the same way. E00.20. This is the second subinterface. After coming in, we still assign .1Q to it first. It is processed for VLAN 20. Then configure the IP address for it. 192.168.20.254. 255.255.255.0. We now have the interface configured. Let's check. Show IP interface brief. We can see now. We do not configure an address under the 00 interface. Then under the two subinterfaces, we configured 10 network segment and 20 network segment. Act as a gateway for two PCs respectively. So let's talk about how they work together. Before we say, just look at the experimental phenomenon. I am now accessing 20.1 from 10.1 here on PC 1. So now can I communicate? Let's take a look. Ping 192.168.20.1. It works now. Cross-network segment. Walked 3 floors. And we also divide the VLAN. We are taking the one-armed route. Let's make a summary. We first send out a data here. Here. Belong to VLAN 10 and tag 10. Released 10 and 20 here. And the default native VLAN of the interface is 1. So I keep this 10 and send it over. Send here. Hand it over to the current subinterface 00.10. It is located exclusively at .1Q10. It is designed to handle 10 tags. Then a subinterface like this. When receiving data, this 10 will be stripped off. So in this 10 it is stripped off. Then the router officially starts processing. After the router is processed, query the local routing table for forwarding. In the routing table you will find the next hop will be VLAN 20. You may not understand this. We'll talk about that later. We know it's coming here later. Before sending down. When sending, it needs to go through the local .20 subinterface. Then put VLAN tag 20 in it. Then send out. Our trunk needs to be released. After release, it came to the access interface with 20. After stripping off the 20, pass to PC2. So let's now look at the routing table. Show IP route. Now we will find out. Now we actually have to go from the subinterface. Because what we are configuring now is the subinterface. Because we are configuring the address for the subinterface. And we are now using the normal subinterface. So it goes through the subinterface. When its next hop matches the upper subinterface, then it will mark the corresponding tag on the subinterface. For example, I query to go to network segment 20. My outgoing interface is now .20. Then I'll tag 20. A data comes in. If the data is processed by the subinterface .10, I'll take this 10 off. So for subinterfaces, an interface to receive data. Strip off the tag. Send data. Tag. Who does this subinterface belong to? We'll strip whoever and beat whoever. And to make an emphasis to everyone. Inside Cisco, there is a capability called ARP broadcast in the subinterface. We just missed a link. PC this sends a data. Here. It requests the MAC of the gateway. Subinterface. The subinterface wants to send an ARP request to the 20.0 network segment. PC1 come here now. Request gateway MAC. The gateway is going to request the MAC of PC2. The gateway is now going to forward data. But for subinterfaces, Cisco subinterfaces can send out ARP broadcasts. Okay. This is also an experiment that I will leave you with today. Finally, let's talk about Layer 3 VLAN. The following configuration does not need to be changed. I just stop this device. Then turn it back on. For this device, just wait and reconfigure access. You can imagine that there is a virtual router in the switch. The router has its own interface. This interface can be configured with IP. I'm in the switch. Configure an IP address for VLAN 10 and VLAN 20 below. As the gateway of the PC below. Let me tell you about the process. The ARP we mentioned earlier. And the MAC address table we talked about today. This requires you to have a very godly understanding. Let's talk about it. How did it work? PC1 now wants to access PC2 across network segments. First it requests the MAC of its own gateway. It wants to send an ARP broadcast request. Send data to the switch. Tag 10 here. Then the switch is actually a fake router. Actually, the switch itself can handle. It's just that routers may be better understood by everyone. The switch itself will disassemble the data packet. After dismantling, you will see 3 layers. After seeing the 3rd floor, it is equivalent to entering the switch after typing the tag here. It will unpack itself. It will see 3 layers. The IP address requested by PC1. It is the IP address configured in this VLAN 10. Then the switch will reply to PC1. The switch is called backplane MAC. That is, there are no MACs under the interfaces of many switches. Only one backplane MAC. It's just a MAC address written on the back panel. For the entire switch. Reply to the PC with its MAC address. After the reply, the ARP is over. PC gets its MAC. Start data encapsulation. When it goes to request, the switch starts sending data directly to PC2. But the purpose of encapsulation MAC is the backplane MAC of the switch just replied. That is VLAN 10 MAC. Just send it. Switch to see the destination MAC is it. It depends on 3 layers. The 3rd layer you want to go is PC2. It checks the routing table. This is its direct connection. Wait a minute, we look at the routing table. It will display VLAN if 20. This is the next hop. For us now. The next hop to PC2 is VLAN if 20. This is a logical port. But everyone must pay attention. A logical port is, after all, a logical. The real data must be sent from the real physical interface. So which interface is it sent from? We will now go and send the ARP request. Request MAC for PC2. So which physical interface is this broadcast packet sent from? How to judge? At this time, the broadcast message. It will be sent from all interfaces that allow VLAN 20. For example, here is the switch below. There is an access interface. Belongs to VLAN 20. This interface also sends. There is a trunk interface. It passes VLAN 20. This interface also sends. All interfaces that allow VLAN 20 to pass through will be sent. Then send an ARP broadcast request. This is called VLAN if 20. In short, you will understand. Even if there are other interfaces are sent. But this data will definitely be sent to PC2. Because it belongs to VLAN 20. Then when PC2 receives this message, it's going to reply. It will reply its own MAC to this switch. Then the switch learns. Now the 01 interface corresponds to the MAC of PC2. It has an ARP table on itself. The record is IP and MAC. It now has a MAC address table on it. Record MAC and interface. So when the data is actually forwarded again, it knows to send out from this interface. What I said may be a little complicated. You must figure out its overall communication principle. That is to say, next hop is VLAN if 20. This is a virtual interface. What physical oral hair? All interfaces that allow VLAN 20 to pass. It's just that this broadcast packet is sent out. Only PC2 will reply. Because the request is its MAC. In ARP, target IP is PC2. Only PC2 replies. Once it's back, data flows through the interface of the switch. Will appear in its MAC address table. So the interface matches the MAC. Simultaneously, PC gets ARP reply. IP and MAC are also matched. Then the IP and MAC interfaces are all matched. Future access PC2. The switch knows that it is sent from the 01 interface. So, although the next hop you see in the routing table is a virtual interface, but actually for the switch, it can find the real physical outgoing interface. If you don't understand, you can take a look after class. It's normal to not understand the first time, but I've made it as clear as possible. Okay. Let's look at the configuration. We open this switch. First, let's look at the VLAN. Show VLAN brief. After coming in, we must still go under the interface. We just deleted the interface. Let's reconfigure. E00 interface. Switch port mode access. Then switch port mode access VLAN 10. Then we enter the E01 interface of the switch. The same. Switch port access VLAN 20. We have now divided the interface. Their configuration is exactly the same as before. Then we know how to enter the VLAN if interface of the switch. Also very simple. Interface VLAN 10. You'll see it here. The sub interface we entered just now is a sub. Now this is an if. This is a VLAN if the interface. After coming in, let's just configure the IP directly. This is VLAN 10. Just configure the gateway of VLAN 10. 192.168.10.254. 255.255.255.0. Then enter VLAN 20. Configure the address directly. 192.168.20.254. No shutdown. Let's now check the IP interface on the device now. You can see it here. 1 VLAN 10. 1 VLAN 20. VLAN 10 is 10.254. VLAN 20 is 20.254. So now the address is matched. Let's just look at the routing table. Show IP route. You will find, although it is a switch, but there is also routing table. We can see a directly connected network segment in the routing table. Is 10.0. This is VLAN 10. This is VLAN 20. So now you will find a data access 20.1 from PC1 to the switch here. It queries the routing table. It will see that PC1 wants to access 20. Then the local outgoing interface is VLAN 20. VLAN 20 is a virtual interface. Specifically why it can go out from the 0/1 interface in the end. Just follow the order I just said. It can eventually learn the interface. That is IP, MAC, and outgoing interface. It can be matched one by one through the local ARP table and MAC address table. Finally, the outbound interface can be found. Send traffic down. Let's do a test. From PC1 we now go to ping 20.1. I can still ping, although this picture has been changed. Device delete to delete. But both of them have been able to communicate. That is, the above device can always help it forward data across network segments and VLANs. This is called mutual access between VLANs. Now many functions are integrated into this one device. And the real interface. Actually, it is an access interface. So actually, for the virtual interface in the device just now. That is, VLAN 10 and VLAN 20. When this data is received, it will be unpacked. When unpacking, it will remove the corresponding tag. When sending data in the future, it will put the 20 tag on it again. This is called repackaging. Then remove the 20 here. Everyone understands the specific concept of VLAN if. Okay. I will now make a summary with you. The purpose of our VLAN division. Not to block their flow. Actually, the main purpose is to make layer 2 unreachable between different VLANs. We just want it to be different on the second floor. Because the overall transmission method of the broadcast is the second layer. Layer 3 does not forward broadcasts. Router interface does not forward broadcasts. So strictly speaking, refers to the failure of the second floor instead of 3 layers. So we are more inclined to do traffic isolation for the second layer. And the broadcast is actually spread based on the LAN. Router interfaces do not forward broadcasts. Let me give you an example. If the router interface forwards the broadcast, the ARP packet we sent, if the router interface also forwards our billions of internet users around the world, everyone sends broadcast packets every day. That's too exaggerated. Therefore, the router interface must not forward the broadcast. Only devices such as switches forward broadcast traffic. The purpose of our VLAN division is to make the second layer unreachable instead of 3 layers. What we finally achieved is to allow unicast. But the broadcast is not working. Normally there will still be some traffic exchange visits. Okay. I didn't expect to talk about VLAN for so long. It doesn't matter. We have a little configuration left for next class. Let's briefly introduce STP. In fact, it is biased for other configurations. Not so much to understand. So it's not hard to say. Most people will find STP difficult. But what we have learned at this stage is relatively simple. I will draw a picture first. This is a typical architecture diagram. Let's not talk about what STP is today. Let's first talk about what problem it solves. Let's draw a few devices first. Draw a few devices. This is a standard architecture diagram. These are switches. Assuming egress, this is a firewall. The devices below are all switches. This is the aggregation layer switch. Below is the access layer switch. Then the access layer is connected to the terminal. There are even PCs one by one below. So what are these devices at the access layer? Assuming this is the equipment in the office on the first floor. Behind this is the equipment in the office on the second floor. This is the equipment in the office on the third floor. Then, if such an environment. This is the operator. We are now going to data access. We are now on each floor. There is an access layer switch. Will be connected to the aggregation layer switch. This structure we talked about before. I won't describe it anymore. So think about what's wrong with this picture. These devices on the first floor are connected to the switch on the access layer on the first floor. The equipment on the second floor is connected to the switch on the second floor. The one on the third floor is connected to the switchboard on the third floor. Yeah. There is a single point of failure problem. The switch in the office on the second floor is connected to the aggregation layer. Only one line. If this thread breaks, we usually don't mean the line either. Usually refers to. For example, there is a problem with its interface or its interface. The interface is actually more prone to damage. But we usually say the line is broken. What we call a broken line. In fact, more refers to the interface has a problem. Once there is a problem with the line, then don't go online on the second floor now. Now connect to the external network with this one line. Generally speaking, the computer room has operation and maintenance. Someone will check regularly. Airtightness is also very strong. Let's talk about a single point of failure. Once this line is broken, the second floor will not be able to access the internet. And someone might have a way. If this thread breaks, just connect the 3 devices below. If it breaks later, the traffic on the second floor is like this. Do you think this is feasible? It won't work. Access layer switches usually have a performance problem. Even terminal. In the future, the lower layer terminal traffic will be aggregated from the upper connection port, sent to the upper aggregation layer device. On the whole, it has no way to withstand higher concurrent traffic at the same time. For example, this is a 48-port switch. Under normal circumstances, the traffic of the device below port 48 is sent upward. Suddenly it's broken. Then its traffic goes this way. And it suddenly wants to send more than 90 traffic. It may not be able to bear. This device simultaneously sends to the traffic all of a sudden. The device may be down. This is an access layer device. Access layer equipment is characterized by cheap. It doesn't perform well. So you can't connect like this. Let it go. Such a network is very bad. If you see a network like this on a person's project, it's definitely not okay to go to an interview like this. Even if you did that just now. What if there is a problem with this device? The 3 floors below will not be able to access the internet. So this is also called a single point of failure. This problem is very serious. So how to solve this problem? I deleted the above. Because we are talking about STP today. In fact, there is no need to draw so many devices. Just to give you a feel for what it means. We can now add another device. Add a device at the aggregation layer. That is, I'm going to put another device here. After that I connect all the devices to it. They are actually connected. But I won't draw this one. Because the NA stage cannot talk about this technology. In fact, there will be other technologies between them. Tell you later. After connecting, you will find, if this line is broken in the future, flow here. This thread is broken. Flow here. This thread is broken. Flow here. This is called multi-line multi-machine hot backup. So we pass some redundant lines and redundant equipment. Realize that a device is disconnected. Just leave this device. A line is broken. Traffic can still go this way. So it's a matter of backup. But this creates another problem. It can improve the reliability of the network. But it also creates problems. Let's take a look. We discussed switches today. For a broadcast packet, the switch, it's flooding. The incoming interface has received a broadcast data. Then it starts flooding. Received a data here. In addition to this receiving port, other ports are flooding. Flooding here. Here also flooding. Still flooding here. I'll be back here. It's just a line. Let's see if the other lines come back. Send this. It also came back. We just looked at the interface on the left. Actually there are other. Still from here. Still can come back. No matter how you go, you will come back. Don't look like it's covered. But they are not the same. Let's not discuss on the left now. Because the right side is actually sending out at the same time. No matter how this flow goes. All switches are flooding broadcast traffic. Then the switch sends a data packet. You will find. It keeps charging. Everyone is sending it. These devices are also the same. Just this one broadcast message is sent here endlessly. This is the problem of packet flooding. It's called endless flooding. Always a broadcast packet. As long as a broadcast comes in, it will send. Nothing on the link. Until the final bandwidth is full. After that the device is down. After the bandwidth is full, the current performance of various hardware soars. Until the device goes down. Bandwidth is not the most important. Important is, after it receives the broadcast message, to deal with. Although the processing method is direct flooding, but also deal with. So the device will fail one day. This is called a broadcast storm. This is the first question. There is a second question. We just learned something called MAC address table. It stores the correspondence between the MAC address and the interface. For example, the MAC address of this host is A. This interface is 1. This interface is 2. This interface is 3. You will find, since a message was generated just now, because it has been receiving this broadcast packet, the source MAC of the broadcast packet is A. When data comes in, the MAC address table of the switch will record. Interface 1 corresponds to A. But when sent back, or this broadcast packet, the switch will record that interface 3 corresponds to A. In the same way. Let's do another. Look. This data packet arrives at this switch from interface 2 again. The switch will record that interface 2 corresponds to A. So in this MAC address table, the storage is 1 corresponding to A. After a while, 2 corresponds to A. Then 3 corresponds to A. This is called the shock of the MAC address table, also known as MAC address table drift. It's all a very bad phenomenon. Our network is for normal business data forwarding. For example, a data is sent. Query MAC address table forwarding. Now in this MAC address table, for a while, A corresponds to 1. A while corresponds to 2. 1 will correspond to 3. Messages sent out in different periods. They are all sent from different interfaces. Amazing. This business cannot communicate normally. After the data is sent out, the host A cannot be found. So you'll find out now. This architecture creates 2 problems. A broadcast storm. One is MAC address drift. Both problems are difficult to solve. It will seriously interfere with our business. Before multi-line multi-machine hot backup, our business traffic forwarding is fine. It's nothing more than a bit of a single point of failure. Less stable business. But now even if the line is broken and redundant, But if the line continues, this problem can't be solved. Since we want to improve the reliability of the network, then it will bring some new problems in the network. We are now going to solve this new problem. We want to keep the network architecture like this. At the same time, new problems arising from the network architecture must be solved. Then we need new technology. There is a technology called Spanning Tree Protocol, called STP. Let's start with a brief introduction. For example, there is a loop. There is a broadcast storm. Then we can now do automatically block some interfaces. Everyday situation. This blocking is not to turn it off, but to mention one more thing. Logical blocking. This interface is open, but it does not forward business data. That is, this interface is not closed. When it sends data daily, still receive. After we run STP, we'll send a message called BPDU message. If this message flows through this interface when sending, this interface can receive. And it also logs information locally. That is, it can receive messages, but it doesn't send messages. Under normal circumstances where our business is stable, it does not send any message. Secondly, this interface does not send business traffic. Any traffic that might loop these, it is not forwarded. So I can guarantee both. Under normal circumstances, this interface does not send data. It also ensures that if there is a problem with the other line, this interface can be automatically up. Then start forwarding. Like a button. If now in the network environment, there is a line forwarding, it can judge whether there is a loop in the network. If there is this port, block it. Blocking is not turning off. When it senses that other lines in the network have failed, then this interface is automatically up. Then start forwarding data traffic. This way it can be achieved without broadcast storm. No loop. It will not have MAC address drift. We can't talk more and more in depth in this class. The STP protocol is not commonly used now. It's not bad, because it actually has to block some interfaces. Everyone should know. This interface is very expensive. Modules actually have overhead. You will find, if this link is not forwarded now, in fact, the other party's interface is wasted. It is equivalent to running an STP now. You will now find, there will be a problem with your device. This interface appears to be, but in fact it does not forward. It's wasted. So in fact, STP is a waste of network resources. So now STP is not very practical. But we still have to learn it, because the algorithm of this protocol is quite powerful. STP is actually design some ports to be logically blocked. Then the port that is blocked usually does not forward traffic, but it will store some packet of configuration information in STP. Once it finds that there are no loops in the network, then the port will be up. Start forwarding data. This is the characteristic of this protocol. Let's talk about how it is implemented in the next class. Let's introduce STP first. STP can simulate an acyclic tree in the network. It will have a sequence problem. A tree must first have a root. Then the root of the tree is called the root bridge in STP. Bridge means switch. The root bridge is the root switch, as a core node of the entire STP. In an environment, which device is the root device? Which device is the root bridge? We need to know how devices communicate. Let's take a look at the content of the courseware. For STP, you see there are 3 devices here. So among the 3 devices, let's go first. Since we are going to build a tree, where is the root of this tree? All three devices have the potential to be routed. Then the choice of this route must have some parameter comparisons. Everyday devices can send some messages to each other. Comparison of size. It carries some parameters of the respective devices. Finally, a root device is elected through the election rules. Same. We also send messages. Select other things through some messages inside. This will be covered in the next lesson. We want to choose root bridge, root port, specified port. These three parameters. We have a message called a BPDU message. This is a message in STP. In this message, we'll carry all the parameters involved in the election. Are comparable. The devices send messages to each other through. Then elect various roles. In the NA stage of STP, it is actually the election of roles. For STP, the difficulty lies in the election rules. This BPDU message is called Bridge Protocol Data Unit. It is responsible for a message that determines the status of all information roles in the entire STP. The entire STP protocol is actually carry out overall communication according to BPDU message. Just like an OSPF hello packet. In fact, there are two kinds of BPDU. A configuration BPDU. One is called TCN. This we will talk about in the next class. But all its messages are called BPDU messages. You need to know this. A message for all status role determination. All role states are determined by such messages. Before we formally talk about the content of this message, let's first look at a few core parameters in it. In the next class we're going to do some data comparisons. These four are the first ones we will mention in the next lesson. In this lesson, let's briefly talk about. First, have a root ID. Root ID is the bridge ID of the root. BID is bridge ID. It's a little hard to understand. There are many STP parameters. And not easy to understand. But you must know. BPDU messages will be sent between devices in the future. For example, many devices in one environment. This is a switch, not a router. They both send BPDUs. Assuming now it is a root. But in the root ID of all switches. At that time, the device thought that the root would be filled in. For example, now the root is device 1. Then in the packets sent by all devices, root IDs are all 1. Both device 2 and device 3 send 1. Prove it now thinks this device is rooted. It also considers itself to be. Then send to the downstream equipment. It will also carry 1 in it. Also consider it root. STP relies on such BPDU messages to maintain the overall relationship. Root will always send to other devices. Other devices will keep sending. It's like picking a boss in an environment. The boss must always tell others that he is the boss. It has been notifying other devices that it is now acknowledging it. This is called BID. This parameter is always the root bridge ID. Let's talk about how to represent this ID in the next class. Let's talk about RPC again. This RPC is short for root pass cost. Refers to the distance from the device to the root. Then for the root. Root self-to-self overhead is 0. How to calculate other devices to root. In fact, it will also be related to the interface. In the next lesson we will talk about. First understand. Let's talk about bridge ID and port ID at the end. This message will be sent down. For example, now this message is sent to switch B. Then if it is the root, it should be filled like this. First root ID is yourself. That is, me. RPC is 0. Bridge ID or yourself. That is, me. Say this is interface 1. Port ID this is 1. This is the message it sent out. Arrived at switch B here. Switch B also needs to receive packets and send it down. Then the message sent by switch B. The route ID is still the switch A. This parameter will not change. RPC will describe the distance from switch B to switch A here. After that, the bridge ID will be changed to itself. This is called your own bridge ID. In the whole STP, all devices are called bridges. So it describes itself. This port ID is its own. That is an interface on switch B. If you received a routed device, that includes routing to downstream devices. It is then sent to the downstream device. Certainly. It's blocked here. Let's not talk about the blocking problem. Assuming it was sent out. It received. Then all this inside is the route. This is the route path overhead sent to that device. Let's take switch B as an example. Let's understand briefly. Let's talk about the rest in the next class. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMo Education. I'm Grolin Annesley from ThinkMo. I hope today's content is helpful to you. See you next class. Bye classmates.